Welcome to the session High Performance and Safe by Design Next Generation Battery Systems for Road Transport Applications. My name is Marta Gialampouki. I'm a project advisor at CINEA, the European Climate Infrastructure and Environment Executive Agency. And I am here with my co-moderator, Manasa Sridhar from IVECO Group. And will guide you through this session. So I will not take a lot of your time because the most important is to hear and listen what our projects will say today. As you already know, the European environmental policy for climate neutrality by 2050 is pushing towards rapid implementation of transport electrification. So with this project, we'll, can we, I think I can change, yes. With this project that are funded in 2022 call, the purpose is to develop next generation battery system technologies for electrification of transport and mobile applications, such as road, waterborne, airborne, rail transport, as well as non-road mobile machinery. The projects also demonstrate increased performances, for example, energy density, power density, and lifetime, as well as safety of battery systems to improve the competitiveness of the European battery industry in the transport market. And also, they develop novel design and process to reduce manufacturing, refurbishment, dismantling, and recycling costs for battery systems. With us today, we have 5 research and innovation actions. They are the 5 projects that you will listen in a bit. And all of them, they are finishing their first reporting period, the first 18 months, so they are in the middle of their implementation. So I would also like to say that all these 5 projects have been generated a cluster that they are collaborated between them in different aspects, and this cluster's name is EU Ingenious, and they are very active working together, which is very, very appreciated because they share lessons learned, having dissemination activities all together, and also improve the whole European battery system infrastructure. So I will start with the first project, which is Extended. Extended will be presented by Maximilian Mellin. He's a project leader in Innovation Hub for BMZ Group. The project title is Next Generation of Multifunctional, Modular, and Scalable Solid-State Battery Systems. Extended is developing efficient, lightweight, and sustainable semi-solid-state battery packs with reduced charging time over 500 kilometers range and a lifespan of 300,000 kilometers. Also, the project features and advanced BMS implementing BMSs for both first and second lifetime application. And finally, Extended optimizes battery systems for multiple applications suitable for EVs, stationary storage, and aeronautics. So I will ask Maximilian to come here and present the project Extended. Please, Maximilian, the floor is yours.
Thank you. So, Marta, first of all, thank you for your kind words. I'm Max, I'm from BMZ, and today I would like to present our Extended EU project. So the title is Next Generation of Multifunctional, Modular, and Scalable Semi-Solid-State Battery Systems. So you can already see one difference to the title in the paper. We focus now on semi-solid-state batteries, while at the beginning we focus on solid-state batteries, which we will talk about. To give you an overview of the consortium, we have 19 partners. I'm from BMZ from Germany. The project leader is RBE in Belgium. And we scattered around 10 countries. And we connect academic institutes and industry leaders. We started our project in June 23 and end in March 26. So we have half time. We just had our review meeting. And yeah, I will show you some results. So what is it all about? We want to build 3 modules based on semi-solid state batteries, which focus on 3 different use cases. So we were asked to show our objectives and targets. For this, we talked to our different partners, and we wanted to illustrate our KPI progress. So as already mentioned, we have some KPIs: performance, for example, a lightweight design, high charging capability, but also aspects like safety, improved safety against fire, external fire, and thermal propagation, aspects of sustainability, the reduction of battery life cycle impact, but also cost and time concerning the manufacturing and the disassembly, and then we also have factors of applicability and dissemination. So I wanted to make it easy, I think, because we only have short time, so I will give you an overview of the results. So what we first do is, of course, when we want to construct our modules for the different use cases, we have to define a baseline and general requirements. So we looked at different use cases, for example, electric vehicles, electric buses. Then, of course, we also have to look at the internal components. For example, you can see here for the BMS, the different parts we need, and for the battery thermal management system. At the start of our project, we designed a first conceptual design of the module, which you can see here on the left. And this we will use to characterize this with different thermal simulation and electrical simulation. I just want to give you here some aspects of the different work packages. So it's not only about to build these modules, but to also to achieve our KPIs. We looked at different solutions. So one is the electrical solution, which include wireless communication. So in our different use cases, we will use actually 3 different solutions for electrical monitoring of the cells. One includes the wireless communication, another also include printed sensors, and one is different to the amount of sensors, also include thermal temperature sensors. Then other work packages include the electrical characterization of the cell, but also electrical and thermal modeling. So in this case, we really use the data we can get from the characterization of the cell and use it for our modeling system. And because one of our KPIs is also thermal propagation, we constructed a reduced scale module testing. So of course we don't want to do all the tests on our 3 modules at the end and burn them down. So we built this reduced scale modeling to learn something about the thermal propagation of the cell inside a module. And in this reduced scale module, we also use advanced materials, special heat spreaders, and heat shields. Here you can see other aspects of our work packages. So in the last months, we made progress. So we updated our design to use more cells. And then we will use this module design to define certain virtual use cases. So as I mentioned earlier, we have the 3 use cases for the modules, but these use cases are connected to energy storage, EV, and also buses. So there we discuss this by virtual use cases. We also performed abuse tests on the cell, which we will use for our modeling. And another work packages is the identification of the key exploitable results. So as mentioned today, in the innovation chain that we have the 3 pillars. So actually we use a technology from pillar 1, which is semi-solid state batteries, and we go in this pillar 2, and we also want to know what is needed to bring the TRL level at the end of the project to higher TRL levels. And that's why we identified key exploitable results which are important in our project, which we discuss then in detail. Another aspect, another work package is, what I mentioned at the beginning was, we don't only want to build the modules and estimate the parameters of the use cases, but we also want to know about manufacturing cost, recycling, and that's why the LDFX methodology was developed, which is in fact a life cycle assessment study in which we will bring information from our project. But this will also be compared to literature values, but we will also bring use cases from our industrial partners. So from BMZ, we will give a EV use case, which we will compare here to show that this approach with our modules has high recyclability and high good dismantling properties. Okay, then I already come to the mid and long-term expected impacts of the project. So what is yet to come? So our goal is to build the 3 demonstrators for the 3 different use cases. We will use different materials which are suitable for the different use cases. We will apply different workloads connected to the different use cases, and then we can test our modules. Another goal of us is to have 3 workshops, which are all planned for this year, and yeah, this is yet to come. And the last aspect is what is important here. So for the EU, how to disrupt. So we want to further optimize the semi-solid state battery system, but also the solid state battery, which we had at the beginning. So I think, as I see the project, it's also an important task to show what are the benefits and drawbacks of solid state battery technology and compare this to lithium-ion, but also semi-solid battery systems for the different applications. We want to evaluate how we can scale up the capacity of manufacturing. And this will be one of the big challenges. Of course, we can also do this only virtual and by this life cycle assessment. And then we want to develop sustainable recycling and second life solutions for semi-solid state batteries. Yeah, and as I promised, I made it short. And thank you for your attention.
Thank you very much, Maximilian, for first the very interesting presentation and also for keeping the time. For those that have questions, please keep them for the end of the presentations. We will have a specific dedicated Q&A session, so you can ask the presenters your questions. And something more here, when you pose your questions, please first state your name and affiliation. So the next project is TEMPEST and will be presented by Jeremy Warren. Jeremy is working in AP Plus RESCOL, and he's working in multi-panel project divisions, and he's the chair also of the EU Ingenious cluster. So TEMPEST has a title as Next Generation Multiple Architecture Battery Systems for Industry. TEMPEST will bring module-free battery systems to TRL5 using AI optimization and lithium-ion capacitor and solid-state cell chemistries demonstrated through 3 different battery times, one for compact, one for large scale, and one for stationary. The project goal is to develop high-performance, safe-by-design, and recyclable batteries for diverse transport applications, including automotive, aircraft, rail, maritime, and stationary storage. Moreover, the project is also working to develop sustainable value chains and exploitation strategies and improve circularity through improved design and recycling methods. So I will ask Jeremy to come here. So please, Jeremy, the floor is yours.
First of all, thank you very much, Martha, for the introduction. My name is Jeremy Warren, and I'm going to introduce to you the TEMPEST project. I will first like to point out that this is a very ambitious project, and there is a lot to cover. So I am going to give you an overview of the most salient results that we have achieved to date, but please don't hesitate to contact me afterwards if you have any deeper questions that can't be covered in the question and answer session. Furthermore, if you have any questions about the cluster, again, I'm here for that as well. So the TEMPEST project is, we tried to spread out ourselves in terms of geographic representation. And it is a project which includes both European and contributions from the UKRI. And let's see. And it is a project that includes now 10 partners from a wide variety. But more to the point, the TEMPEST project's objectives principally turn around next generation cell technologies. And we use both liquid electrolyte and solid-state cells in this project. Our goal is not to focus on one specific battery type or one specific system. What our primary goal is to develop a set of technologies that are translatable across a wide variety of battery cell types and potentially into the future, maybe even sodium, potassium, other types. And so that's why we tried to integrate these two types as the foundation. Again, we want new architectures so that we can optimize space, we can optimize weight, but also to improve the circularity through better methods for assembling and disassembling it end of life, recycling the materials, recovering the metals, recovering the graphite and reusing it, and using new models to optimize the performance and optimize the mechanical behavior of the batteries, and finally to develop sustainable value chains. And one of the things I want to point out about this project is we are unique amongst the projects presented today in that we use composite housings. And this itself has been one of the challenges, but also one of the technological opportunities here. So our overall goal is we want to achieve at least 70% recyclability in the batteries. We want to reduce the cost of manufacturing by about 30%. We want to increase the performance by about 15% and reduce the weight of the overall pack by about 15%. This latter point, we have actually already been able to demonstrate that, at least in the gravimetric cell-to-pack ratio, we've already been able to demonstrate that we've completely exploded that. We're at around 80% now. And that is simply by shifting from aluminum or steel housings to we are using helium composites. We have been able to dramatically reduce the weight. So, first of all, in the results, I'll briefly introduce to you the different types of packs or different types of cells we're using. So you can see that we have Gen 3 and Gen 4 in here, and we have already started testing and evaluating the cells to establish essentially the data baseline for everything else that will be done. Now, one of the important things is as I pointed out, we have composite systems. These composite systems have different behaviors in terms of what everybody accepts for how a housing is going to behave if it's metal. Crash resistance, corrosion resistance. A lot of these things change dramatically, especially since we're using helium composites. So you have to consider how is this going to behave when it's in somebody's car. So one of the things that we're implementing is a structural health monitoring system. Structural health monitoring system will continuously monitor the composite system, detect if there is a fissure, and essentially communicate back to the battery management system to tell, for example, the driver of a car, oh, you've got a problem, you need to go back and get it to the service station as soon as possible. So this is a guided wave system that is currently under development, and these are our preliminary results that show that we can already, essentially, what I will point out is that these are the preliminary results, and they are currently being refined and optimized to improve the detection accuracy. But the point is here, we already have a solid proof of concept to show that we can detect defects, okay? And this will be completely integrated into the PAC system at the end of the project. The other thing I want to point out is that one of the goals is to be as open as possible. So the firmware for this SHM system, as well as the BMS, will be open sourced, and it will be available soon. One of the other things we want to address is improving thermal management. So we're developing thermally conductive coatings for assisting in transferring heat from the cells to the cooling system. These are deposited by cold spray. These are the prototypes that we have right now. In addition, we're looking at physical and thermal protection. So first of all, we've done modeling already to evaluate impact resistance of the housing to impact such as rocks from the bottom. We've already done modeling to also address, set the computational baseline for when you have, for example, the impact of a pole or some other large object against the housing. We're also, to complement this, we are working on impact and abrasion-resistant coatings to go onto the packs. In addition, fire is always a significant issue. So to help address this, we are developing two different types of coatings in the project. The first one is a fireproofing coating for the inside to essentially auto-extinguish any cell fires as they occur. It's a one-time use coating, but it's something that we're currently developing. The second one is a flame-resistant coating, which is designed to protect the outside. Say, for example, there is a fuel leak in a crash. There's a fire. Basically, what it will do is will swell up and protect the housing. So it'll give it that much more time to resist the heat. We are also looking at circularity. Okay, one of the things that's also important is at end of life, how do you address this? First of all, through using LDM composites, we're going towards a composite formulation that is essentially by design more recyclable. Second, we're using debonding on command adhesives, which by themselves, once they're deposited, they have a very strong strength. But at end of life, simply through the application of heat, they become very easy to despond. You can basically just pull them apart. The other aspect is that once you've got these apart, the most important thing, the critical raw materials aspect, is something that needs to be addressed. And that is the next thing that we are addressing is through methods that are developed by National Institutes of Chemistry. We are looking at methods for using hydrogen routes to both recover and transform the graphite, as well as to recover the metals. Okay? So the idea here is to have a circular pipeline for recovering the materials at end of life. So what are the long-term, the mid to long-term expected impacts? Well, there's a lot to go through here and a lot to unpack. The most important thing is first of all, we want to address the volumetric cell-to-pack ratio and the gravimetric cell-to-pack ratio. Now, the volumetric cell-to-pack ratio you can improve simply by getting rid of modules. That's one of the easiest approaches. And so we're using a cell-to-pack ratio to address that. Second, the gravimetric cell-to-pack ratio. That's commonly one of the more difficult areas to address. In this project, as I said, we've addressed it in large part through moving towards composites. That's given us a huge boost in weight savings. Then one of the things, I haven't talked about it here because we haven't gotten to it yet in the project. We are going to develop a system called energy storage as a service. And I'm not going to go over it in detail here because it will take me a while to explain. But the basic concept is to introduce new economic models for the supply, the use, the recovery, and essentially develop a circular economic model to encourage both manufacturers and users to participate in a circular economic model. We are also going to engage further with the JRC to help work on developing new standards, work on new policy. And we are also in the process of developing training programs for upskilling. And as mentioned before, I'm the chair of the EU Ingenious Cluster, so I will be happy to address any questions for that. And finally, I want to talk about circularity. As I said, we're trying to take a holistic approach to this, not only taking the pack apart, but also addressing the issue of critical raw materials. And then our current estimation is that we're looking at possibly a potential of about 75 million euros in terms of economic impact on the 5th year after the project, and around 80 new jobs. We'll validate that through LCCA in the project. And thank you.
Thank you very much, Jeremy. I have to put down, I'm a bit shorter than you. Also, if you would like to learn a bit more about our presenters, you can find short CVs in this wonderful paper copy. So you can see also some more information about our presenters. So the next project is VERSAPRINT. So this project will be presented by Lisa Lugracia. She's a project manager at CEA. So the project is about versatile printed solution for a safe and high-performance battery system. The project advances climate-neutral transport by innovating battery systems through 2D, 3D printing directly on components. Also, key solutions include efficient thermal regulation, enhanced safety, lightweight casing with recycling capability, and control exhaust gas management. Moreover, a decision tool will optimize configurations validated at TRL5 with prototypes for automotive, aeronautics, and waterway transport, alongside simulations for other transport. So, Lisa Lu, the floor is yours.
So, hi everybody. Thank you, Martha, for the nice introduction. And let me start here. So, welcome again to this next presentation about the European project called VERSAPRINT. So, as Martha said, and we can easily see from the title that it's about versatile new solutions for safer and high-performance battery system using printing techniques. So before that we dive in the technological aspects of the project, let me introduce you quickly this project. So it is a project with 10 partners with an interesting mix of researchers and industrials. It's a 3 years project, as Martha said before, and we are now reaching half of the project, so we do have some nice results that we are happy to present you today. And you can see here the advisory board that advises all along this project. And as it was repeated now many times by Martha and Jeremy, we are part of this cluster, so that if you want to know more about it, don't hesitate to contact us. Now, coming into the objectives of this project, we are aiming at developing new versatile solutions at system level. So it means we don't look at the chemistry of the cell, but everything that is around, so at a higher level, like cell unit and module level, and when it's written cell level, it's around the cell. So you will see what we mean by this, that we are trying to 3D print components around the cell at the cell surface. And so we are using printing techniques to allow fast prototyping and to have more freedom of creativity and to develop more creative solutions. We have also at the center of the project, we are developing a decision tool that will help us to combine these new technologies that we call building blocks. So we develop different building blocks, and this decision tool will help us to combine them for a specific application. And you can see that we also have a wide range of applications here, so automotive, aeronautics, waterborne, and others. And the goal will be to see and to optimize the new technologies for a specific application. And a bit more in detail, today I will not present you all of the building blocks. When it's called BB, it's building block. I will present you just some of them where we have interesting results. So at cell level, just around the cell, we develop the building block 1, that is microchannels for an efficient thermal management and to cool down efficiently the cell. And we 3D print this cold plate in silicon directly at the surface of the cell. I will also present you the building block 2, that are sensors that we also would like to print directly at the surface of the cell to sense temperature and detect hydrogen. At cell units level, it means to connect different cells together. We mainly worked on bus bars. And I will present you some interesting bus bars that we developed non-welded, that we can, that are easy to assemble and disassemble. And at module level, we work on lightweight material for the casing and also on an exhaust gas management system to drive the particles and the gas out when there is a thermal runaway event. Here you can see the KPIs, so the objectives we have in our project, and you can see that they all target and try to answer the challenges that batteries are facing today. So they aiming at increasing the safety. We have talked about it before, that it's we have problems with thermal runaways, for example. So we do have technologies that try to answer safety, to increase it, to increase performance, to increase lifetime, and the circularity, working on sustainability of the technologies we develop, while trying as much as possible to reduce the cost. Now, going into the details and the results we can present you today after 18 months, we developed, as I said, the building block 1, that are microchannels that you can see here on the left. It's a silicone plate that we 3D print directly at the surface of the cell, and that cools down very efficiently the cell. And what is interesting to see, here you can see the thermal losses at 1C and 3C, so with heat generated, and we can see that we are keeping the cell at a very nice low temperature. And this building blocks will have an impact, so increase the safety, because it will delay the thermal runaway event by cooling down efficiently the cell. And it will also have an impact on the lifetime, because the conditions around the cell have an impact, so the temperature, the pressure, and other conditions have an impact on the lifetime of the battery. So it increases the performance and the circularity. Here it's actually a small video. I don't know how it works to click. Okay, no. Okay, it's starting already. So it was actually a few months ago, so now it's much more optimized than this, but it's to show very quickly the fluid that is circulating very nicely with no losses, no mechanical losses during the flowing of the fluid. And this we will print, we are printing actually right now directly at the surface of the cell. The second building block I am sharing with you is the sensors. So these two sensors have been developed, are being still developed in the project. They are having an impact on the safety, because we want to prevent thermal runaway or to detect it. So the first one detects the temperature directly on the cell, and the second one is to detect hydrogen, so which is a gas that is produced when there is a thermal runaway event. And both these sensors have been developed with water-based inks that makes them more sustainable than commercial sensors. We can see for both of them a nice linear answer. So for the temperature, we can see a decrease, a linear decrease with a nice slope that makes the sensor sensitive. in a range of temperature of 0 to 100 degrees, but we do face challenges. We are still working on it. We face challenges in the negative temperatures. And for the hydrogen sensors, we can detect very low amount of hydrogen, so it's very precise. And we also are still working on it because we face challenges here in the response time. And another building block, so at cell unit level, it means when we connect cells together, it's building block 4. So that is an easy to dismantle bus bar that is non-welded. So you can see the principle of this bus bar on the left here. We have we have this lower part that we weld. We do weld this part on the cell directly, and then we only have to connect and to clips the two higher parts on top of this welded part to connect the cells together. And the plastic part on top is insulated. And with this technology, we almost completely disappear the electricization and shortcut risks during assembly and disassembly processes. So it has a very big impact on safety. And the last building block I'm showing you today is the building block 7 that is at system level. So considering, for example, on the left scheme, you can see 12 cells together. And it's a system that connects all the exits of the cells so that when there is a thermal runaway event, it collects the particles and the gas that comes from the thermal runaway and drive this out of the system in a precise location by also reducing the temperature of the gas exhausted and filtering the particles. And this can prevent this gas and mix that comes out to take fire. And you can see on the right the test that we have performed by overheating a cell. You can see the heat gun, and you can see the gas coming out in a precise location. So the gas didn't come out at some point anywhere in the casing, but was driven in a precise location outside safely. You can also see that it doesn't take fire because this is thanks to the filtration, the pre-filtration inside the system of the particles. And what is interesting to see in the results here is that the measured temperature at the cell where the thermal runaway happened was 1,200 degrees, and the temperature of the gas that came out was divided by 2, so 600 degrees. And we actually do have even better results right now, but it's already a very promising result. Now, all these building blocks and technologies we are developing in VERSAPRINT, they are answering and the targeted objectives from the European Circular Economy Action Plan of 2020. So mainly what we are doing is trying to increase the lifetime and to reuse and make easy to disassemble, assemble, so to ease the processes at all the phases of the technologies. And we are also working on eco-design and to lower the impact, the environmental impact of our technologies. I will show you a little bit more about this in a second. And also VERSAPRINT contributes to implementing the conclusion of the European Council, so mainly developing versatile solutions, as I said in the beginning, for different transport applications. So we will be able to use different technologies for different applications. The decrease of the fossil dependency and improve the health conditions, of course, and increase the performance and safety while reducing the costs. Now, talking about sustainability, I take this opportunity today to show you some results we also obtained and concrete methods that we have used in VERSAPRINT to tackle sustainability and to improve the sustainability of our technologies and batteries in general. And we have used two different approaches, eco-design guidelines that we give at each point of the life cycle of the technologies. So we have used on one side LCA tool to assess the environmental impact of our technologies, and we also gave guidelines, eco-design guidelines, at each steps of this process for each of the technologies. And I'm happy to share with you one result. We have obtained more, but due to the time restriction today, I just show you an example of what we have done and the results we have for building block 1. So it was the silicone cold plate that we 3D print on the cell surface. And we compared it with a classic solution that is a cold plate, metallic cold plate in orange. And the building block 1 we have developed is in blue. And here I show you results of life cycle analysis only for the production phase, so raw materials and manufacturing. And what we can see is that we don't have a clear impact, or we don't have better results compared to a classic solution for the production phase. And we also, it's interesting to see that we also have a big impact in the stripes here. They show the platinum contribution. So in the silicone that we have used, there is a very small amount of platinum that was used to produce and to make the silicone, but that actually has a big impact, environmental impact. So we also see that we need to work and to find another process for the silicone we are using. But when we take the use phase and end of life phases into considerations, so not only the production, but the use phase also, then we take in account the reduction of weight that we have compared to a classic solution, and then we have a lightweight material, and so less consumption and less environmental impact. And this is what we see in the results. So for not all, but some of the impact categories, we see lower environmental impact for our technology. And this is what we have done for all of the technologies we have developed to make sure that they are, to assess at least and to try to make them better than other commercial classic solutions. I have other results. If you want to talk about it, don't hesitate to come to me, and I will jump to the conclusion. You have here our social media, and we also have deliverables that are public, so you can check our results, and you can always contact us for more information. I will be happy to answer and to contact you about this. And thank you for your attention.
Thank you very much, Lisa Lou, and thanks all the speakers for keeping the time. It's very important. We are already 5:14. Okay. So one more thing that I would like to say here is that all our projects are having TRL 5 to achieve at the end of the project, which means that their demonstrators, technologies, etc., will reach TRL 5, validating in relevant environment and not going above. So it's good to remember this for your questions and answer session. The next project is NEXTBAT. So the project will be presented by Mikko Filati. He is research professor on electrification of transport at VTT. So the project aims to establish reliable and innovative battery systems, as well as to enhance recyclability and interoperability. The project will incorporate battery management systems at the cell and system level and integrate innovative electronic sensing and actuating systems to enhance battery life. Finally, the project will contribute to decrease the carbon footprint of the battery system by decreasing production cost with high recyclability capacity of both hardware and cell components, introducing along the production chain. So, Mikko, the floor is yours.
Thank you so much, Marta, for the introduction and the organizers, of course, for inviting me here. It's a pleasure to be here to present as the coordinator of the NEXTBAT project, where we stand more or less halfway through, as all of the other projects here. And I will not even try to cover everything that we're doing. It's just a selection of a few of the results that are emerging more or less halfway through. And I should also say that we have in a very intensive period of the project as we are finalizing, as we'll go through shortly, prototyping tracks that we will then demonstrate and show the innovations and work on the innovations in a tangible, concrete way. So now is kind of the time to do that. So let's start with some quick facts and on the project as a whole. So as the others, we belong to the cluster of EU engineers. It's a 3.5 years, 42-month project with partners from, let's say, from an axis across Europe. More or less half of them industrial partners and half of them from research. We run until end of November 26 next year. Grant amount is about 5 million, so project in itself slightly larger. This is a road transport conference, but I should also say that we are, as some of the other projects here, addressing batteries as a key technology for a range of applications. We have industry from aviation side, waterborne, also off-road machinery, and many of these, of course, as we know, use the same technologies, same solutions as such. But then, at the same time, we see a lot of requirements, application-specific things that we need to take into account. And the technology solutions are developing at the pace, such a pace that we really need to be able to place the different technologies, solutions, innovations in their context, so as to choose the right pack system solutions for the end user or the use case we're dealing with. Right. So NEXTBAT, and let's start with the objectives, the scene that we are addressing. Of course, we see similarities with the sibling projects here. So this is nothing very new I can bring to the table. So one by one, on safety assessment, this is quite one of the central themes in the call or in the projects that we go. So safety assessment methodology, and now we want to scale from battery cells. We're not developing battery cells as such, but we need to understand how they work quite fundamentally. Cells, subsystems, packs, modules, and all the subsystems that are involved. So how to assess that and analyze and understand the innovations that we have therein. Then, as said, requirements, technical specifications of the battery systems, be it waterborne vessel of different kinds, and there's a huge range in that segment only, off-road and so on, so the harsh use applications and so on. So we've spent quite a lot of work working around that area and of tech specs, duty cycles, profiles, load profiles, working profiles of battery systems specifically serving those different applications. And only in road transport we can see many things, for example, fast charging, being strenuous on the charging side, and then various types of stress factors affecting lifetime. And this is also what we want to understand, how to maximize the lifetime performance across lifetime. Then on the third point, design and manufacture battery prototypes, and this is kind of the tangible corner of the project. We are pushing 2 prototyping tracks and the innovations therein. Also, we want to be in the design space, conceptual, reflecting back to the actual requirements and the use cases applications. Software is a key part here, and that can be applied and used on many approaches up to a digital twin strategy in the management and co-simulation of an operating road vehicle in its use case. But it's a very valuable tool and approach for high-fidelity simulations for optimizing thermal management, conceptual tools to really start with from top-down designing and looking into different solutions. Number 5, hardware for batteries designs and management. I'll get back to that with a bit more details on the hardware. Demonstration, validation of the prototypes, and through the prototypes also the design approaches, architectures, concepts that we're working with. And of course, lastly, promote the market uptake, look into the diffusion paths, how the bigger picture looks in terms of batteries being deployed into various segments. So that's the setting. And now let's just delve into some of the highlights or the chosen results where we stand at the moment. We set out to kind of look into technology from battery cell being, of course, a key component of any battery system. So we need to understand that sourcing cells, analyzing cells from the market, we were aiming at solid state battery packs or modules, struggled a bit to find solid state batteries from the market, and I think this has become quite clear for many actors here. So we made a compromise, as we heard also extended, using semi-solid state cells, and this is kind of in between there. We are kind of wanting to push the specific energy towards 300 watt-hours per kg at system level later on. We will not reach that in NEXTBAT here, but we still want to analyze what that kind of technology will mean from the battery system level side. So there were generation 3B in more or less in the domain where the technology is at the moment, and 350 watt-hour per kg is the semi-solid cell track for the prototypes aiming at higher energy density. So we've done various chemical testing, fast charging, cycle life, calendar life, aging, various types of quite standard testing. Safety testing at cell level, I get back to that a bit later. It did end up a bit later in the slide deck. Safety testing with a canister. We're working on immersion cooling at the second prototyping track, a bit more on that shortly. Safety matrix for testing. Now we work at the cell level, but later on the safety validation and testing will be pushed up to module level. And then the cell technology roadmap, as we know that there will be a lot of developments coming up. Another big, from another work package here, starting top down and on design tools, how to approach the system architecture, system layouts, and there will be various combinations of these. So we have put up a library of duty cycles from the different types of road vehicles and others, conceptual design tools to take into account thermal design aspects, electrical architecture aspects, cell performance, duty cycles, and various configurations, excluding mechanics, because we are not reaching at TRL5 to really mechanical packaging of packs. But this gives us a solid background to really work around the different concepts for technology and systems, and also place the different innovations that we're working with into the analysis framework. A bit more on the prototypes. As said, 2 prototyping tracks. One aiming at high energy, so using the semi-solid state cells. And what, let's see how to get back here. This one, good. The laser was this one. This is for prototype 1. It's a kind of not design frozen module yet. So we'll stay at module level 48 volts, 14 cells in series, 1 in parallel. Packing of those, liquid cooling, BMS, and then packaging that at the module level. Whereas prototype 2, we push the power density to a higher level, and including two innovations here. One is the immersion cooling system. So what is not shown here, so we're also working on the casing because we need pressurized system, and it's also fiber-reinforced plastics combined with joining with aluminum, and I think then the reference will be maybe a steel casing or aluminum casing there. So that's the weight reduction element there. A second innovation there will be cell level monitoring, EIS, for advanced diagnostics to really work on safety related state of temperature, for example, and then we have a maximum effective thermal management system to control that and really to be safe on not to run over into the thermal runaway side. Large activity in the high order models, and I think especially we have Barcelona Supercomputing Center being the main partner there, CFD modeling, and really to analyze the flow geometries and cooling. Thermal runaway simulations included, so that's a high fidelity. We also have a number of physics-based models training AI surrogate models for cells for performance degradation and so on, and that also will be leading to once the final design of the prototypes is fixed, so then digital twinning of those and matching that with the test sequences, validation sequences, both normal operation and then the safety. And now let's see how the it's a simulation video here. I'm not completely sure how to start it. Yeah, it does. Yeah. So just showing this is prototype 2 and seeing a sequence of the thermal flow and how the temperature gradients develop as part of the design space. We also done a sub-element like cell level simulation, choosing the electrode or the oil and some of the elements there. And I think this is done. There's another one, fluid velocity, that was the temperature first. So this is also validating at this stage when we're finalizing the designs of both prototypes. This is on P2 on the thermal side. I believe it's maybe, yeah. Just a couple of words on the cell testing. So I started with the cell selection. We've looked into available cells, and we'll be following the roadmap type of approach later on, just to place well, as part of the comprehensive safety approach. There's an inherent safety of the cells. Then there are intermediate subcomponents like thermal barriers, thermal management, and the management system as a whole, and then the structural elements and so on. So this is part of the inherent part, internal of the cells. So we've done destructive testing on all of the cells that have been in the matrix for screening. And later on, when the prototypes, 2 of each design will be manufactured, so they will also go to the safety validation and testing later on during the second period here. And then this is the last result I picked up. We're working on the battery passport, like usage analysis, and this is also supporting the LCA life cycle assessment, life cycle cost analysis. So using the recently published regulation or standard on the battery passport, how to utilize the data. And this is linked into usage profiles. And also we expect with the digital twinning and the laboratory experiments really to bring specific information and interface this also with the BMS, which is of course an integral element of the safety approach as such. Just a couple of words to conclude here on the impact side. A funnel to create impact. This is also our internal process that we follow, identifying the key results. Of course, this is what each partner in the consortium is working. Right now, we look internally into the business innovation potential, and later on this will lead to the business plan and also creating the individual exploitation tracks. And currently, as said, we are more or less, as we delve deeper still into the actual innovations that we work with, charting out the individual tracks. And then on the bit longer, mid and longer term benefits, contributions to EU policy and so on. So of course it will build on the tangible results, outcomes, exploitable results, and then contributing to the roadmaps, creation of a longer time view, advancing safe battery technologies, and specifically bringing the innovations towards the more application-oriented, higher TRL work. Performance, sustainability metrics, I think there was already also shared, that are more or less joint and common on EU policy level. And then there's the industrialization, industrial strategy, and also we want to push out, besides our own industry partners to support that, but also reaching out through the cluster and also wider to the community and stakeholders. And by the way, we are just forming and initiating the advisory board targeting industrial players, and we have a couple of positions open. So if there's some industry player here who is in the thematics and interested, so please get back to me so we can maybe get you involved as a stakeholder following the project more closely. The contacts are missing from here, but NEXTBAT is the name of the project, so I'm sure you can find the website and the contacts there. We'll be happy to get in more details and share the results with you. Thank you.
Thank you very much, Mikko. Now we are heading to our last project, last but not least, BATS. So it will be presented by Iosu Sentoya. He's a business developer for European projects at CINEA. So BATS aims to develop a high-performance, safe battery system for transport applications, using a safe-by-design approach to mitigate risks throughout the battery's life cycle. The project will create a modular battery system with outstanding electrothermal performance, mainly for off-road vehicles and maritime transport, reaching TRL5 with innovations in thermal, electric, and mechanical design. The project will also enhance battery sustainability through modular assembly, disassembly, automated disassembly techniques, and second life applications in semi-stationary products. So, Iosu, the floor is yours.
Okay, so thank you for the introduction, Marta. As I said, let's go to the next slide. Okay, so as it was said by Marta, I'm coming from CINEA in San Sebastian. I'm very glad to have this opportunity to disseminate what we are doing in this project. We are, I think I'm not doing it right. Which is the bottom, please? Oh, this is one. Okay, so we are the younger of the group, okay, because we started half a year after the other ones. So we just started 1 year ago, so in January 2024. As you can see, safety is key in the slides that you will see, and you will also notice that many of the aspects and goals that I will mention are common to the other projects, because of course we are we fall in the same topic. The funding you see is about 5 million euros, and the project duration is 3 years. Regarding the partners, we, as it was said by Marta, we have 3 use cases. 2 of them come from FPT, a maritime application and an all-road application, and the third one comes from MIBA battery system, which is a semi-stationary use case. And let's say that the core concept also is based on one of the ideas from MIBA battery system, and the other partners will enhance this and improve it. So here I try to summarize in some words the objectives we have. So as I said, the first one is to design a battery system that has this design. It is useful for different type of markets or segments. On the other hand, the idea is to follow the safety by design principles to design the battery pack, and at the same time, we have to keep this balance between cell-to-pack and modularity that you all know, which is difficult to reach. You will see which is our approach. Regarding some figures, the idea is to reach a cost reduction of about 2% for the battery system with respect to the baseline defined by our colleagues of MIBA battery system. And in terms of volumetric and gravimetric energy density, respectively, it is an increase of 15% and 12%. On the other hand, fire was something that was, I think, explicitly written in the topic and requested that should be taken into account. And not only, but it is one of the specific cases that should be considered. Mainly in our case, it is coming from the thermal runaway. And the idea is to reach a UCAR hazard level equal or less than 5, depending on the case. And of course, define countermeasures. On the other hand, regarding the process of manufacturing, the idea is to reduce in 50% this cost during the manufacturing phase, and build some assessment tools for the disassembly and recycling phase. On the other hand, of course, we need to develop a LCX in order to prove that there is an improvement with respect to the baseline. And another objective of any European project is the dissemination, communication, and identification of key exploitable results. So regarding results, I just focus on the results that has been, let's say, we have some progress that we can show. As I said, we have just started 1 year ago. So the first challenge was to define even the drive cycle, because in the automotive sector we have the WLTC. Formerly we had the NEDC, but in this kind of segments, off-road, maritime, and Second Life, there is no specific, let's say, standard profile so that it could be compared. And this was something that I remember it was also highlighted in the workshop. That, by the way, I highlighted there. That was that we collaborated thanks to the EU Ingenious cluster together with the JRC, BEPA, and 2.0. And in that workshop, one of the things that was highlighted is this lack of information or guideline for this, as well as guidelines about safety and guidelines about abusive tests to be applied to this kind of vehicles. I take this chance to remember that here we will try to do some standardization activity on these fields, drive cycles, safety means that we are introducing in a design, and that is why we participated in this workshop, and we are also in contact with the ARPA. Another result is based on the impedance spectroscopy, that we are trying to use it to assess the quality of the weldings between the bus bars and the cells. You will see afterwards that this project, because I did not mention it, but you will see it in the pictures, it's about the cylindrical cells. Okay, indeed you can see it because of the format. 21700 was the baseline, and that was. That it is defined by MIBA battery system, but this project is about 4695 cells. So these, thicker ones. And the technology, by the way, is NMC, advanced NMC. Okay, So here we realized that with some samples which related to the 21700 thin bars, we were not able to distinguish, or we could not see any difference between a high quality welding and a bad welding. But in December, we realized that when we started to already to create samples of the new bus bars that are related to the thicker, to the higher current related to these 4695 cells, we could use it as an element to assess the welding of this bus bar and cell. And this is something that the idea is to be implemented in the production line, so that this could, let's say, enhance the cost and improve the production. So this is something that it's working on. It's a work in progress. This is one of the important milestones that we have. It is, as it was mentioned by some of our colleagues, we also in the plan it was to create a downscaled module design, so that we can do some iterations with respect to the simulation that we are already doing. So this is such a downscaled module. It has been already. We are now assembling this. The colleagues of MIBA are going to assemble this, and in March it will be tested at CIDETEC, and there will be a deliverable, and this will be a good reference to be compared with the simulations that we are running, and create some iterations. It is likely that we will produce another one during the year to go on with these iterations. On the other hand, on the electronic architecture, the goal is to build a wireless BMS. There is already a master-slave structure BMS that has been successfully tested with quite a low power consumption. Regarding the cloud communication, basically we are going to improve an existing interface and select some hardware for this cloud communication. And one of the aspects that will enhance the safety is the internal short circuit tracking. So basically, this is a work that it is mainly done by CIDETEC. We already did this analysis fully on pristine cells, and now we are going to do it on edge cells. So it is to detect the thermal runaway, or sorry, the internal short circuit before it happens, or early in the very preliminary phase. Another point is to design a power switch based on silicon carbide technology. And on the other hand, VUB will be, or it is focused on a interleave bidirectional DC-DC converter that they have recently finished, a preliminary design. On the other hand, here you have, let's say, the CAD file that we have finished. So this is quite advanced. It is already according to the boundary conditions of the use case, especially the marine application. So the idea is that we have a concept, which is we started with the marine application. The idea will be that this is modular and scalable for an off-road application. It is an excavator. And then on the other hand, as you see, this cell-to-pack modular concept, it is mixed this way. So on the right, you see that it is a cell-to-pack. So you have several cells in a battery pack. On the left, we have a battery system. And in this cell-to-pack concept, there are even bricks that could be reused for a station application. Okay? So this way, we are trying to mix the cell-to-pack concept with the modular concept. So this is about the result. I did not mention that, of course, we did all the cell characterization activities and abusive tests and so on in order to reach 1D models, electrothermal models, that at the moment we are scaling up to 3D electrothermal models that are the ones that we are going to compare versus this experimental data that we will get from the downscaling module. Regarding the outcomes, they are quite generic. I mean, it's because in the first year, so this is what we expect to get. It is so the idea is to reach the next generation battery system with increased performance and safety for transport and mobile applications. And this could be divided into what I said, transfer this knowledge to different type of vehicles and segments, and on the other hand, implement the safety by design approach into the usual R&D process, okay? And the other outcome would be to reduce, as I said, the manufacturing, refurbishment, dismantling, and recycling cost of battery system. And this would be done by taking into account these aspects from the very beginning of the design, and with this modularity concept, and by proposing some automated disassembly system and a tool to assess the reuse and second life of the battery. Finally, in the longer term, the idea is to increase the competitiveness of the European battery ecosystem. As I said, the cells are European. The idea of the pack is also coming from one of the European partners. So we hope that we can push this and extend this concept to the rest of the markets and products. As I said, the advanced NMC technology that we are using, and this link to the second impact, we are promoting the European cells, and we are using them, and we are collaborating with an external manufacturer in order to include it in our project. And then the other important aspect is the impact we hope to reach it is to make a product that is attractive for the citizens and for any other business, in terms of safety, in terms of reliability, and in terms of cost, by enhancing the design, energy density, volumetric energy density, and the safety measure that we have mentioned. And that's all.
Thank you very much, Jos, for the presentation. Someone should have scared you, all of you, to respect the time, because we are very ahead of the time, but this is good. So now we are going to the Q&A session. So I will pass the floor to my co-moderator, Manasa Sridhar, who will moderate the remaining time. So, Manasa, the floor is yours.
Thank you very much, Marta, for passing the floor to me. I prefer to stand after all that while of sitting. First of all, yes, I'm very glad to be here moderating this session. And I think it's a very good time for these projects to be presented, because it was mentioned before, it's the half-time, and it's just exactly the right moment to, really to start to see the results and, speak about the achievements that have been made so far. So these projects are addressing the actions contributing to the the partnership SRIAD timeline, particularly focusing on high-performance, safe-by-design, next-generation technologies targeting transport applications. And we can all agree that we have seen some really promising results that have been shared. I want to first, I'm sure there are many questions from the audience, but just to start with maybe slightly provocative or stimulating question from my side. What are the challenges that you have faced so far? The results, they look very promising. The KPIs, ambitious that you are targeting to reach at the end of the project. Of course, keeping in mind that it is going up to TRL 5. So there is still some journey to get there. And I'm interested to know, what have been some of the challenges that you have seen and what you foresee as well, as you progress towards project completion. And, okay, it's a little bit of a long question. In the first plenary, there was also the talk about the innovation cycle and how it is absolutely crucial to transfer all these results along this pipeline, so to say, to bring it to deployment. So I would also like to address to the panel, what are the challenges that you see there? And if you would like to point out to some specific developments on the side of, the policy, the infrastructure, the stakeholders, the skilling, that would really be necessary in order to translate these technologies into a market-ready product. So, any volunteers?
I can start. So from our side, for example, one of the biggest challenges has been to match the specifications and requirements from each use case, because it is very challenging to try to be modular. I mean, propose a design that could be so useful for so different segments as the ones that at least in my case, I think you too, some of my colleagues as well, maritime, off-road, semi-stationary. It's difficult to fulfill that. So I mean that there are advantages and disadvantages in this approach of modularity. This was the challenge in this case. I'm not saying it is the solution. The solution could be to separate every segment and optimize the design for every segment. But since this was the challenge, I mean, this is really challenging, and that is why I highlighted, for example, that was difficult to agree also in the profiles and charging strategies. And related to this, for these segments, there is very low guideline on which kind of standards, which kind of tests should be used. It is not like in the automotive sector in which everything is already on track and the guidelines are very clear.
Yes, please, Miko.
Now it's working. Yes. Thanks. I had 2 points, and you more or less brought up one of them, so I'm happy to maybe just continue a couple of sentences on that. Definitely, I see this is a no one solution fits all type of situation, the width of different requirements, applications, and so on. So then we end up kind of in a discussion how to be generic and specific at the same time, because there are a number of different innovations that we are addressing, several of those, but not all of them. And I think kind of these projects combined, I think we can cover the space pretty well. But then kind of how to make a methodic approach that we can do both to the maximum extent, to be generic enough to be saying that and deal with the kind of questions, does this work for aviation? Does this work for off-road machinery, which is really one of the harsh use cases, waterborne, and the road transport being the topic of today. So that's maybe one of the challenges, and at least I don't have the full answer yet, but we'll keep on working on that. Maybe another concrete challenge that we have was sourcing of the cells. As we would, the battery cell, it's really the heart of any battery system. And when we want to push towards the next generation, then it would be really nice to prototype with the solid state or whatever, sodium and so on. And these are not really so easily available. So we kind of lose part of the picture when we cannot put the new cell technology into the context of the new solutions, technologies for the system design. So that's one of the aspects, and we will continue to work on that as well.
Okay, then I will go on. I'm on the line. So totally agree with what was said before. We also, I mean, it's also linked to the fact that we are going from TRL2 to TRL5. So yeah, it's hard to find solutions that fill all use cases. And for us, I mean, we also had the objective to find versatile solutions that can apply to versatile technologies, so it's especially cells. And we also are trying to find, for example, solid state to make the solutions applicable to solid state cells. And we are still looking forward in the next periods after our project to find these cells so that we can adapt our solutions to this. And for us, we also have a specific, we met a specific challenge that was the comparison. As we are going from TRL2 again, we are developing very creative and innovative solutions, and we cannot compare them to what exists today. So it's hard to assess and to validate and to assess and to compare their performance compared to other solutions that do not exist yet. So I'm thinking about the solution I've presented you, that is the exhaust gas system management, that we have, we do see a very big advantage of this solution in terms of safety, for example, but it's hard to compare it and to evaluate it compared to other solutions, as it's a very new, innovative TRL 2, 3, 4 solution.
From my side, at least in our project, I think one of the most important things, in addition to everything else that has already been brought up, is also the issue of fragmentation. Right now, regardless of whether you're talking about the automotive industry or the maritime industry, or aviation is a little better in this regard, there's a lot of fragmentation. If we talk about charging standards, it's one thing. Essentially, everybody has their own approach. And this makes it a lot harder to focus our efforts towards one common goal. So, for example, if I talk about battery management systems, everybody has their own different approach, and very often everybody's got their own secret sauce towards optimizing or that, this kind, and essentially it just makes it a little bit harder to implement new approaches and new designs and have a much wider impact, because then they need to be custom tailored each case and to each application. And so one of the things that we're trying to do, at least from our side, is to give back to the community. So as I said, our battery management system is going to be open source, and we're going to work to engage with the community over the long term to see what we can do to help bring in contributions and make it more reactive to the community. Same thing for the structural health monitoring system. That's new in batteries. So we're trying to make it open and work with people to make it a more generally open and easily adoptable standard. But that, the same thing applies across a wide variety of the parts that go into batteries, the cells, the packs, and everything. And I think what's most important for Europe in general and industry on the European scale is to start to come together towards a more common approach. Because by doing that, that means it makes it easier to develop new technologies. It makes it easier to integrate them in and to move more rapidly and more dynamically. Because everybody's working off the same common platform and understands things on a common approach. And I think that's probably the biggest challenge for us right now, is that all of us, even in the cluster, we have our own visions, we have our own approaches towards this. And it's already, a challenge for us, because we're each running our own projects, and when we submitted this projects, we had our own goals. But now that the projects are running, we're saying, oh, well, you're doing this, and you're doing this, and you've got your own approaches, and we're all using different cells. And already, just amongst the 5 projects, we're saying, okay, how can we start to come together to work together on these common goals? And that's already a challenge. And imagining that at the EU level, at the European industry level, that's a whole different game. But that's something that does need to be addressed. And so, at least from my side, I think that's probably the biggest challenge.
Yeah, I think a lot of important things were said. I want to point out here a little bit the connection between the things. We also had the problem in going from solid-state batteries to semi-solid batteries. And these KPIs we had, I think we all have kind of ambitious KPIs. These were connected to a solid battery which kind of believed exist. And I think it's also part of our task to not be in a dream world to show the perfect battery will come in 5 years. This is exactly what we see. We see semi-solid batteries on the market. We evaluate also chemistries like sodium or LFMP, advanced cathode, which we also don't see at the moment, which have their own problems. So at the end, we will see batteries suitable for a certain application. Yeah, you don't need extremely high charging for storage applications or something like this. So there we have to look and have to learn what we can achieve in specific applications. Thank you.
Thank you very much to the panel. Indeed, it's quite a delicate balance between being generic versus specific. Of course, being generic, having standardized technology that can be scalable, that is, going to reap the award of economies of scale, but at the same time, really addressing the specific challenges of different applications. It's not easy, but we need to find some common approaches. We need to converge together because that's how we can really maximize the impact. So we have 44 minutes to be really precise. And yes, I would appreciate if each of the persons in the audience can introduce themselves before addressing the question. So the mic is with Jesse. Yes, please.
Yeah, thank you. My name is Daniel Buro. I'm working in innovation management at Volkswagen. And my question goes to basically the project that deal with integrating semi-solid state cells. I appreciate that you're dealing with this topic because I believe if these cells reach market penetration, it will come not only from the cell level advantages, but it must come from system integration advantages. And often discussed is one point definitely thermal behavior. Will they allow us to get rid of some of the packed level TP safety measures? Another thing is, will we be able to simplify cooling, for example? So I understand that these answers to these questions may be the final result of your projects, and it's maybe too early to conclude. But I would be interested in your assumptions and expectations on these 2 points.
Sorry for that. Yeah, you more or less stated our research question. Thank you for that, and it's one of the essential ones. As said, we will. That's kind of the best available cell we're working on right now, and that I cannot give specific answers because we are running the test sequences right now. But this is the very, very question. What does the next generation cell, when we use that as a system, what does it actually mean in terms of thermal management, electrical management, safety designs? Do we have the barrier walls? What is for example, stresses and strains, expansion? There's so many things that play back to mechanics of the pack, thermal management, thermal design, electrical design, the management systems. Do we have other diagnostics methods, for example, for solid state or semi-solid state? What is the difference? So we need to really go quite deep in there. So this is the essence that on that track of development, and it, of course, we are halfway through. If we manage to get hold of some additional into the matrix that we continue to watch, like the road mapping type of thing. Partly we can address that also in the laboratory, I hope so, to be able to be generic in that, but also specific to the, and having one semi-solid state cell, it doesn't mean that all of those are the same as we see in the state of the art. So, yeah. But that's the one of the main research questions that we pose here.
Yeah, just to, in my case, we are not working on semi-solid. It's advanced NMC, but as was mentioned by Mikko, the semi-solid state technology has some other issues related to the swelling, and so the mechanical system, we know it from some other projects. It could not be just a foam that you are putting inside in case of a pouch cell, for example, inside the battery pack, but it should be a really dynamic system, which is much more complex than the current static systems, so that the cell is behaving in their suitable range of pressure. So it's a matter of making numbers and LCC. In order to know if the advantages in the simplification of the thermal system is compensated or not balanced by the mechanical complexity of the new system. And unfortunately, on the other hand, the semi-solid technology is in the infancy. There are just 1-2 technologies In Europe, maybe one. In the United States, a couple of them. That's all. The type of technology that I guess my colleagues have in hands, it is not the more mature. So I guess that they are already facing problems about the behavior of the cells.
Yeah, if I can add one further thing, just from our side, we're using the solid state design we're using is. Sorry. Yeah, from our side, the design we're using is advanced LFP for the solid state cells.
So are these cells from European manufacturers or procured from outside of Europe? Now, the second question on semi-solid and solid state cells, usually they are supposed to be safer by characteristics. Some even claim that the battery systems do not need any thermal management system. What's your take for that, and what are your findings so far with the characterization results? Thanks.
Yeah, from NEXTBAT side, we sourced those cells from China. We couldn't get hold of such cells from Europe. So that's a fact. It's not so nice, but we would have, of course, preferred the European manufacturer. Hopefully it will improve in years sooner than later. And then on the performance, we see some of the aspects. I didn't show and share the tentative results slide yet, but we see some improvements there. So some of the scenarios that we tested, they show better performance, and this is also to be validated. And I maybe should not jump the gun to give all the results here, but yeah, we see some benefits. In some areas, some of the areas we reach quite similar temperatures, so it might depend slightly on the test scenario that we run.
Yeah, I think we have the same situation. I know that, of course, cell manufacturing in Europe is difficult, but I hope not that one part of the problem is that people think, okay, let's wait for the solid-state battery and then we can start manufacturing it. Yeah, so it's also important to look at this small developments. You ask about the difference between solid-state and semi-solid state a little bit, and the question is if the solid-state battery really has this better, don't need a thermal management system. There are also thermal propagation tests of solid-state batteries which have particle blasts and extremely high temperatures, liquid metal, so we have to be careful, we have to be specific.
And if I can just add from the TEMPEST standpoint, our batteries come, the liquid electrolyte cells come from a manufacturer in England, and the other ones the solid-state cells were provided by ABEE in Europe. What we've seen is kind of a mixed situation. I will point out, as I mentioned before, that for solid-state cells, you have extra considerations to take into account. In addition to what you mentioned in terms of the safety, we know that you have to keep them under compression. In many cases, you have to preheat the cells to reach an optimal functional temperature. So it's a mixed bag. They have their advantages, but it needs, it's not the perfect solution. And I think we'll also see this moving into newer chemistries, such as sodium, potassium, calcium. Everything has its advantages and disadvantages. So, take that for what it's worth. We're doing what we can to, bring these newer technologies, but, as with everything as we move forward, it's all about finding the little challenges that comes with each new technologies and doing our best to adapt and evolve to them to bring them to market as safely as possible.
No, in my case, it is not solid state. It is advanced NMC, but it is from a European manufacturer.
Yes, so as I said, for us, we are still waiting for the second period to find European manufacturing.
Thank you. Yes, please, Cicis.
Thank you. This is Amaras, Aristotle University in Thessaloniki, Greece. I was ready to ask the same question because I was a little bit confused. I mean, where do the cells come from? And I read again the call, and the call was asking for advanced lithium-ion batteries or solid-state batteries. And actually, yeah. And actually, there was this discussion before. I mean, they have to be from a European manufacturer, actually. And this is maybe not the case. Nevertheless, would it be an idea, I'm turning to the European Commission now. I mean, this is a cluster, right, that responded to the same exactly call. They looked at different approaches, or they developed different solutions. Would it be an idea or also a help for the others to come up with a final overall table that would list all the different technology, particularly as regards the batteries, because that's the heart, the battery cells, I should say, the pros, the cons that everyone has looked at, the way they were approached, like safety issues, and all those things, as a final product for those who will continue afterwards, right? It is, the presentation is fine. I do understand all the difficulties in what does it mean to be in the middle of a project and everything. However, compacting this information, I think it would be extremely useful for the follow-up calls, actually, or if there are no calls at all afterwards for a few years. Thank you.
Yeah, I think you can hear me. Thank you very much for your suggestion. It is very important. First, I would like to comment on the topic. Indeed, this topic was not on the development of the cells, but the cells are just purchased as components, so they are used as components for the development of the battery packs and modules. And of course, we have to comply, as you already know, in the Horizon Europe with best value for money and availability, of course. So in order to continue with the projects, we need to see what it is best for the projects and what it is a requirement for the call and for the topic. It is very, very important, the suggestion that you have already made. We are very fortunate in this cluster and in these projects because all these 5 projects are tackling different use cases. So this is also a very important aspect. So we have the aspect of road transport, of waterborne, on off-road machinery. So the first impression is that we can indeed do, as cluster, a very good summary of the different use cases and also indeed of the different aspects as safety, requirements, etc. So this is very important, and they are also in the same, more or less, same maturity. So it's, at the end, it will be the outcomes of all the projects that will come out. So it is very important. Thank you very much.
And if I can just jump in as the kind of a sensible chair of the cluster. No, I'll put on my cluster head hat. At this point, since all of us are more or less through the halfway point, what we've been doing at this point is a lot of initial development. And so our focus, for the most part, to this point, has been very much internal development and getting the foundations going properly. But we have already been having a lot of just general exchanges on, exchanging lessons learned. Not too much on the technical standpoint right now because we're still, getting things, as I said, the foundation set in point. But that's one of our goals for the second phase of these projects is to start exchanging on a technical point to talk about our lessons learned, to talk about our difficulties, and also to establish this output that can be, as you said, beneficial for Europe in general, because that's one of the key outputs for all of us is what do we give back to the community. So absolutely agree.
I wanted to add that we already have started together to communicate on our results and the objectives of our project all together in workshops where we invited a lot of different partners and industrials in particular. A lot of them came, so it was a very successful event, and I'm quite sure we are going to continue on this point and communicate all together to any partners who is interested, not only industries, but others too. So it's ongoing, definitely.
From my side, maybe I have a more pessimistic idea. I don't know to what extent could be, the experiences could be shared, but I don't know to which extent could be transferable. For example, it has nothing to do with a cylindrical cell with a pouch cell. Of course, a pouch cell and a prismatic cell are, let's say, neighbors, or are more similar, you can say. Somehow linked to something that I wanted to say at the beginning when I talk about the matching. I think that, again, talking about common platforms and so on, first of all, I don't know if that's going against the competition. And second, I do believe that concepts as, for example, what we are proposing in BATS, in which a company or a group of companies with a common business could create a product that is useful for different segments, even if taken individually, it is not optimal. This way you can reduce a lot of cost. You can as much as you reach the safety level that is required by a market and the cost, even if your requirements in terms of energy density, volumetric density are not the best ones. These kind of approaches with this kind of clusters of companies that have in mind different segments with a modular idea could be something that I think it should be analyzed and studied.
Sorry, maybe.
Well, one moment, yes.
Yeah. I totally agree with you, but these are public projects at the same time, and somehow they have to come up with something which is usable by the public. Now, what the business decisions are going to be on the basis of the results is a different story. I think I fully agree with you, but this is a business discussion towards a different target.
Yeah, but it is not a matter of copy-pasting what is done in a European project. The idea is to give guidelines. So we can give guidelines, or approaches are examples, and of course we can give guidelines. What I'm trying to say is that it is difficult that we give many common guidelines. It could be the case that we are giving some common guidelines, but since the approach is totally different, and even the shape of the cell, even the nature of the cell is different, I mean that I would like to be realistic and know which is the extent in which you expect a common idea about.
I never meant that. Never meant that. No, I just want the information.
If the idea is to share the experience,
bit,
it could be very interesting.
That's a different story. Yeah.
Yes, Mikko, please.
I think we are in the pre-competitive domain here, and that's in a way it's a safe playing field here, and the expectation, I fully agree with that. We should share as much as possible. Of course, there comes the competitive barrier, and especially the industries don't want to go beyond that. That was stated in the opening session today. But I think tomorrow there's a session on solid-state batteries. I think we could think about cluster of clusters also to kind of bring in additional how to make the battery research ecosystem really work and benefit each other. I think that's kind of could be a fast track already to bring the insights into this group here and so on. So I think it makes a lot of sense, like conferences like this, really and thanks Zisis for lifting this up. I think it's an excellent proposal. How to really to make it work in the best way. I think this is Commission and CINEA, of course, leading the way, and at least from our point of view, I would be happy to collaborate as far as we can.
Just one final thing, if I can add it. One of the things that we've already discussed, and this is something that we're going to be working on moving forward, it's not obligatory for everybody, but essentially, as each of the projects releases data packets through Zenodo for publication, that kind of stuff. Essentially, one of our goals will just be to produce a collective newsletter to say, okay, EU Ingenious at this point in time has released this set of data for this set of data for this, and essentially just a better way to more collectively inform the European community in general that, this has been done, and to engage more directly.
Thank you.
Hello, my name is Mohsen Akbarzadeh from Flanders MEC. One short question for the TEMPEST project. The volumetric energy density of the solid state in your slide was, I think, 1,000 watt-hour per liter. Can you elaborate a bit more about the technology? Is it oxide, sulfide, polymer, and also gravimetric energy density? And one question for the VERSAPRINT. What's the reason of using mini-channel cooling plates between the cells? Because it just adds extra weight. It makes the system complicated for disassembly. What was the reason for that? Thank you.
From my side, to be clear, I don't want to get into too much of the precise details of the chemistry, simply because at this point they haven't been cleared for public release. In the TEMPEST project, our standard way of operating is we understand that everything by default is for public communication. However, we also understand that there is a certain obligation for confidentiality and sensitivity for certain information. And so, as part of our data management plan, we say, okay, is this cleared for release? Is this under embargo? Okay? And so there are certain things that are cleared for release. For example, the battery testing data for the lithium-ion cells, the Gen 3 cells, that has been cleared for release and will be released on Zenodo shortly. However, certain technical details related to the solid-state cells themselves, they're still under embargo, so I can't communicate those. My apologies.
Okay, so I will try to answer your question as good as I can. So the microchannels, it's a technology that we thought about for very power-demanding applications. So it's not fitting all the technologies. It's building blocks that we are building and that we want to apply in specific applications. So, for example, fast charging or things that will release a lot of heat. There is no glue. We managed to do a formulation on purpose so that it fits and it sticks a bit to the cell surface, but there is no glue and there will be no other materials in between, so it will be easy to disassemble. We also thought about this dilemma, of course. And yes, it's all I noted for the answer.
So there is no thermal interface material between the cell?
No, we also worked on the thermal contact and to see if it's actually taking the calories out and it's working very efficiently.
Okay, thank you.
Exactly.
Next questions from
Did I answer your question? Okay.
Maybe I have one more question. So most of these projects, you have mentioned that when you develop a design methodology, you try to future-proof it, anticipating the new trends, the new technological developments that will come up. And in many of the projects, there was also mention of making multiple prototypes based on different chemistries. I'm wondering if you are also considering battery systems that incorporate, let's say, a combination of cell chemistries. there are some studies, it could offer some advantages. I just would like to know what is your thoughts on that. Yeah.
I will say from our side, we haven't considered it. It's a very interesting idea. I could say that, without giving a huge amount of details away, that one of our demonstrators that we're looking at, we could theoretically evaluate the concept because there is room in the configuration to put both. We would have to do some major retooling of the internals of the demonstrator, but I don't see why it couldn't happen conceivably. Insofar as the rest of our technologies, as has been pointed out, they've been designed to be pretty much universal in that regard. So it could be something that could eventually be tested. Probably not within the scope of the project because we have enough on our plate, but it's a good idea.
Yes, Miko.
Yeah, brief comment from NEXTBAT. I think so far we are dealing with, let's say, single technology modules or prototypes. And I think the kind of the experimental, tangible, physical work will stick with that. However, we do have, I did share it today, maybe a next event somewhere. So we have an activity we call virtual prototyping, where we intend to kind of pick up from the individual innovations and work across and really scale up. Now we have a 48-volt module, but many of the systems are going to 800 volts or post 800 volts fast charging and whatever reason. So really the virtual prototyping should, and we expect it to kind of add inside. And that activity, why not hybrids combining like power dense and energy dense components, for example? That might be one of the areas. We haven't really decided yet, but thanks for the input.
The reaction, yes, please, Maximilian.
Yeah, just from my side, also from BMZ, we looked at different new chemistries. I also saw that there are already even some A or B samples with mixed chemistry on the market. I think it will also be important to evaluate this. From my beginner chemical level, I would say that for me it's difficult to understand that if we combine two chemicals that we get both benefits. It would be also that we get both drawbacks, right? So, and that will be also, of course, yeah, but especially, and I want to go a little bit further, as you can see in our project, we go to a stage where we want to have electronics on cell level. So we want to get more and more to know about the cell in their whole life. And I would say, for example, if you look at the deintercalation process, and then you have LFP and NMC mixed at the same time, it would be extremely hard to evaluate what is happening inside the cell. So then we need the development on all sides together, then it will become interesting.
Thank you. I feel the energy is slightly receding over time as we approach the end of the session. Maybe I have one more question. Not too technical, but nevertheless, I think it would be interesting for us to know. So this is a research and innovation action, and most of the projects have a duration of 3 years, some 3.5. The next step, would you want an innovation action again for 3 years, or maybe 1 year of incubation? Of course, no. We are speaking in front of the Commission, so we want to be ambitious and we want to do the best we can. Let's say, by joining forces, we spoke about convergence and we spoke about how we want to really collectively bring all the knowledge together to accelerate. So to go to deployment, tier 8, 9, how many years do you see, from where you are and extrapolating to, to bringing into a product?
I have two answers for your question. So if I talk simply within the framework of the TEMPEST project, okay, we focus, on Gen 3 and Gen 4. Okay, it is logical and proper that there be a follow-up project at the scale of an innovation action to translate those results to market. If that doesn't happen, I would consider that on some scale more or less a failure, in the sense of the project comes to its end and we're at TRL 5, but we haven't been able to translate those to a market impact. And in my sense, that then is essentially some sort of a failure to bring those. Maybe there's other projects for that, but essentially, that's the logic for that. However, as I mentioned before, our goal here is also to kind of have universal applications. And so there is also a need for a research and innovation to explore how do these technologies behave with the real cutting-edge cells, such as sodium, because eventually we are going to have to abandon lithium. Lithium is not, from a critical raw material standpoint, something that is sustainable. And technologies such as sodium and calcium and other cutting-edge technologies, they have their inconveniences, but from a critical raw material standpoint, they are the way to go. But I can't tell you, if we're talking about, how the thermal runaway behavior is going to be, if, how our systems will function in those kinds of things. And so, yeah, that's going to require another, essentially, low TRL examination of the situation.
Clear message there, Jeremy. Thank you.
Just shortly, so one of our work package is to show what is needed to go to higher TRL levels. That's why we looked for different key exploitable results. So this is part of the project. Then maybe hopefully with European cells or fully working solid-state batteries or potassium, or let's see. But that we be open and be careful what we can expect from new technologies.
So from VERSAPRINT side, I completely agree with the comment that Jeremy did, and it's also similar for us. So we have some technologies that we started at TRL2. So some of them were really successful, and we can see a fast implementation, and we can see an easy business case that, of course, requires another whole 3 years of work. But some of the technologies also would need more time also because it started at TRL2. So we faced challenges that we didn't expect it. So this also has to be taken into consideration, that we would need maybe for specific technologies, maybe in another 3 years for this one, but some of them were more successful. But yeah, it's also, what we have talked about in the beginning, with the solid state cells, we still didn't do what we were supposed to try to make it as versatile as possible. So we need the technology to work on it. So as soon as it's there, we will be able to finally work on it. But this also, has to be taken into consideration.
Yeah, I think the colleagues here said it already very well. But maybe just to add, besides concurring, so just your original question on the challenges and the multitude of applications and the use cases and the varying requirements. So I think all of these use cases need the follow-up projects, and I think it's a kind of we need it, I think, as a community. So let's keep on going.
In my case, I will give you my wish list for one. So since we are finishing at TRL 5 and we are not reaching, we are going to build a 5 to 10 kilowatt hours demonstrator, that's all. The idea would be to scale up to TRL 7 to build a battery system. Something that it is weak, at least in your project, it is to deeply analyze the production of that battery system, how to improve it. and also deeply analyze the disassembly process and recycling activity, because it will be just a starting point what we are going to do, very partial activity, but in order to, let's say, to fulfill this circular approach, we would need another, let's say, 3 years project in order to fulfill all these aspects optimally.
So thank you very much to the panel. And with this, we are almost 2 minutes. I know everybody's eager. Almost 2 minutes over the time. And yeah, so we will see all of us tomorrow at 9 a.m. There will be more battery sessions, one on solid state, also on Thursday there will be more. So looking forward to further interesting conversations. So thank you, everybody. Have a nice evening.